Okay, let's dive right into this explainer. Today, we're tackling a genuinely fascinating engineering challenge, controlling massive electrical power at ridiculously high frequencies. If you've ever found yourself wondering about the exact hardware that drives advanced medical imagers, heavy-duty industrial cleaners, or precision actuation systems, well, you're in exactly the right place. We're going to break down the whole process, from design and simulation straight through to real-world prototyping of a high-voltage, high-efficiency power amplifier.
To really wrap our heads around the sheer scale of this challenge, we have to ask ourselves a rather terrifying question. How on earth do you safely control 300 volts switching at 2 million times a second? Seriously, think about that. In the world of power electronics, pushing that much voltage at that kind of frequency, that's basically an open invitation for thermal runaway, aggressive electromagnetic interference, and just completely melted components. You can't just slap some standard off-the-shelf parts together and hope for the best. This takes meticulous, ground-up design.
And that brings us to the core of the problem, the actual payload we're trying to drive, the piezo ultrasonic transducer. Now, as you know, this isn't just a basic resistive load like a light bulb. It definitely doesn't behave like a standard audio speaker. It is a highly reactive, resonant load. To generate the exact physical vibrations needed for something like medical ultrasound, it demands absolute electrical precision. If your amplifier introduces any noise, any ringing, or instability, your transducer simply won't function. It's as simple as that.
So here's our roadmap for today's explainer. 1. The piezo power problem. 2. Simulating the solution. 3. Prototyping the hardware. 4. Op-amps and filters. And finally, number 5, testing the limits.
Let's kick things off with Section 1, the piezo power problem, defining the harsh requirements.
All right, so meet our villain, the target specifications. Now notice how these numbers interact with each other. We need an output of 300 volts peak to peak, which is roughly 106 volts RMS, across a 25 ohm load. That translates to pushing up to 6 amps of peak current. But here is the real kicker. We have to maintain bandwidth from 1 kilohertz all the way up to 2 megahertz, operating at a 10% duty cycle, and it needs to accept both square and sine wave inputs. Designing an amplifier to do all of that without distortion? Yeah, that is incredibly tough.
Moving right along to Section 2, simulating the solution, validating in LTspice.
Okay, because those target voltages and currents are just so dangerously high, we absolutely have to transition into software before we risk frying any physical components in the lab. The engineering team explored a Class D or high-voltage push-pull amplifier topology specifically for its switching efficiency. To survive the brutal spikes we'd expect to see in LTspice, methodical component selection was crucial. They went with IRFP460 MOSFETs mainly because they're high speed and can handle over 400 volts drain to source plus 10 amps pulsed. To actually drive those MOSFETs, they paired them with IR2110 gate driver ICs to give us that ultra-fast switching and necessary isolation. Throw in some RF-rated capacitors, low ESI inductors for high-frequency signal integrity, and precision sense resistors to feed a negative feedback loop, and you severely cut down on total harmonic distortion.
Now for Section 3, prototyping the hardware, building the PCB in Altium Designer.
Transitioning from software into the physical realm, we have to remember one crucial thing. A perfect simulation means absolutely nothing if your copper traces instantly vaporize. The PCB design workflow here required strict discipline. They used a 2-layer board to intentionally separate the high and low voltage sections. They utilized star grounding to completely squash electromagnetic interference. For thermal management, heavy copper pores and heat sinks were integrated directly around those hard-working MOSFETs, and perhaps most importantly, all trace widths were calculated strictly against IPC 2221 standards. You have to guarantee they can safely carry those 6 amp peaks without, literally catching fire.
Up next is Section 4, op-amps and filters, the theoretical building blocks.
To really grasp how this massive amplifier maintains signal stability, we actually need to step back and look at the unsung heroes of the circuit, the operational amplifiers. We're talking chips like the 741 or OP27 that condition our weak initial signals long before they ever hit the power stage. We generally configure these in 2 main ways. Because op-amps have a nearly ideal input impedance, meaning they won't drain the source signal, they are perfect for this job. An inverting setup gives you a 180-degree phase shift, providing negative voltage gain based on your feedback resistors. On the flip side, a non-inverting setup scales the signal up without flipping the phase at all. These are the fundamental tools we use to precisely scale our waveforms.
But wait, there is a massive catch when you're operating in the megahertz range. Op-amps have speed limits. We call this the slew rate. It dictates the maximum rate at which the output voltage can physically change, and it's usually measured in volts per microsecond. Your typical chip might be limited to, say, 0.5 to 2 volts per microsecond. Defining and managing this slew rate is just absolutely essential when you're trying to push a clean signal at 2 million cycles per second. If you try to push a square wave faster than the slew rate allows, well, it just degrades into a slanted, trapezoidal mess.
So, to protect the final power stage from all that high-frequency garbage, the engineering team combined these op-amps into active filters. They utilized low-pass filters, specifically a second-order filter which gives a much sharper frequency roll-off to ensure only the desired bandwidth passes through. They also brought in level comparators, setting a strict voltage threshold of, say, 2.5 volts to strip away ambient noise and output perfectly clean logic highs and lows. By leveraging these active filters, they guaranteed that only pristine, noise-free frequencies would ever reach our high-voltage MOSFETs.
And that brings us to our final section, Section 5, Testing the Limits, Real-World Validation.
All right, so all the theory, the simulation, and the layout work is finally done. It's time to hook our Altium prototype up to an actual piezo transducer operating right at its resonant frequency in the lab. The ultimate question here is simple. Will the board survive, or is it going to succumb to thermal runaway and just pop a component? It's the absolute moment of truth for the entire architecture.
I am thrilled to say the lab results were phenomenal. Under the oscilloscope and the thermal cameras, the system achieved a safe, highly stable peak current of 5.9 amps. That is right near our absolute 6 amp design limit, and the board handled it gracefully without suffering from any thermal runaway.
Even more impressively, the efficiency didn't just fall off a cliff. The system maintained an overall power efficiency of over 85%, all while operating at a blistering 1 MHz frequency. Pushing that kind of power at that high of a frequency usually results in terrible heat loss, so hitting 85% efficiency here, that is a massive win for the thermal management design.
These final test results really beautifully summarize the success of the entire project. They achieved a perfectly stable 300-volt peak-to-peak output using both sine and square waves. The frequency response stayed remarkably clean, showing minimal gain loss all the way up to 1.8 MHz. And crucially, especially for driving a piezo transducer, there was absolutely zero oscillation or ringing observed anywhere within that bandwidth. To truly prove its endurance, they let it rip for a full hour continuously, yielding zero thermal drift and perfect frequency stability.
By bridging the gap between rigorous LTspice simulation and incredibly careful Altium PCB layout, this team created a highly capable 100-watt power amplifier. With this robust foundation now proven and tested, the only question left is for you. How might you scale and adapt this exact high-frequency architecture to conquer your own engineering challenges in medical imaging or next-generation actuation? The blueprint is right here, just waiting to be built upon.